Because as we studied before, alpha has to be plane wave. Right? And then we can see immediately that is phi has to be A over R exponential j omega t minus kr. Now we remember that the omega is the how in the, omega expresses how fastly the sphere is oscillating, and the k certainly describes the number of waves per unit length. Okay, therefore this term essentially expresses phase fluctuation in space. Okay. Now our job is to determine A that satisfies this boundary condition. Right? So let's calculate the velocity using this velocity potential. That is, UR is dpdr. And we found that R is located in two different terms. One is 1 over R type. So if I take a derivative first, then that will be A over R squared and minus. And then I have to take a derivative with respect to R over here. That gives me what? A over R, and then minus J and the minus K. Therefore, I have plus JK. Right? Means wrong or yes? Okay. So in Indonesia, when you say means yes. Oh, okay. Okay, and plus, and I write minus J omega t minus kr. Okay, that is velocity at R at arbitrary time. I feel very safe because he's looking at my text, so whenever I make a mistake, he will inform me, right? So, okay, thank you very much. So he's a sort of monitor. He's monitoring me. Okay. But you are listening what I'm saying, right? Okay, physical interpretation.
The dimension of this is the same. I mean, the
dimension of velocity potential?
Yeah, like we don't know what is the dimension of potential, right?
That's a good question. What's the dimension of this? That is velocity, right? Right? That is velocity. Therefore, dimension of phi is velocity multiplied by the length scale. Oh, interesting, right? Can we see it? Can you see the velocity potential? Yes. As soon as we got this, we plot it in a computer. We can see it. Right? Fluid mechanics guy. What is a streamline? What is a streamline? Same potential, but different notation, right? Psi. Huh? But what is the, for example, when you have a streamline, when you draw the line that is perpendicular streamline, what is it? That is potential. Whew. What is the significance of using streamline? If you take a derivative with respect to streamline, that indicates the velocity. So if you have a streamline, and if you see the streamline, then you can see how the flow is flowing, right? Fluid mechanics people, they don't have a T in fluid mechanics. No compressible wave. But we are handling very sophisticated fluid that is compressible, therefore that is oscillating. But in fact, we are handling very simplified version. But this is a good starting point, right? That's a good excuse. You can, of course, use Navier-Stokes equation. Maybe this guy will familiar with this called LES, large eddy simulation, and so on. But the frequency that can cover using that kind of computational scheme is very low. But we can see the problem, unlimited frequency, even though it's sort of approximation, right? Okay, so rearrange this equation, give me A, and I have 1 over R squared plus jk over r exponential minus j omega t minus kr, and the velocity at r equal a should be a minus 1a squared plus jk over a exponential minus j omega t minus ka. That has to be same as this. Therefore, this is u0 exponential minus j omega t. Therefore, I can argue that A should be, A is what? U0 divided by minus 1 over A squared plus J. Is it right? K over A? My monitor, is it right? And you cannot see it because the text did not show the detailed derivation, right? And you may ask me, why you do this detailed derivation? Why? Because this is the only time that we do the derivation, right? After we do the derivation together, then we will examine the result, right? That means I will not, you found the error, right? Oh, that's good, because I feel that there should be some error, because I always make an error. Where is it? JKA? Yeah, I didn't finish yet. In progress. I didn't make an error yet, but I'm ready to make an error. Okay. And then I have exponential plus jka, therefore I have minus jka.